Ooh, and the camera moves a little bit. A little too much. Sorry. Is that cool? Yeah, all right. So let's check it out. Section 8.5, that's today's the last graphic day. Well, for trade. So we're going to start with the graph of tangent. I'm going to have you fill in some of the blanks. And I'm going to be using some of the new notation that you probably didn't use in your trig class, but we've now been using in trig. So let's do a quick reminder. So recall that we defined tangent as we had the unit circle, or at least the way we defined it here in class. You got your radius in standard position on the positive x-axis, and it rotates by some angle theta. And then we have that terminal point, x comma y. And so we defined the tangent of that angle theta to be what ratio? Y over x. And from what we've discussed, y, we're also calling that sine of theta, and x, we're calling that cosine theta. And then maybe this was discussed in your previous trig class, or maybe it wasn't. But another way of thinking about this here is that your radius is a, think of it as a line that's connecting the origin point with the point x comma y. So if you think about the line crossing through the radius, it has a slope according to whatever tangent of theta. The tangent of theta, graphically, or at least on the unit circle, you can also think of it as the slope of the radius. Okay. Here's where I do need my ghetto ruler here. Okay. So you can think of the y as the rise and the x as the run, where you rise by that y coordinate here and you run by that x coordinate there. You can think of it as a slope, this tangent value. So here's where we're going to use some of the new notation that we learned in this class to specify this a little bit. So here's where I need your guys' help. So as we're going to use arrow notation, okay? What I mean by that is we're going to see as theta approaches pi over 2 from the left, and then as theta approaches pi over 2 from the right, remember pi over 2 is right here at 90 degrees. I want you guys with your classmates to double check, what is tangent approaching? Or look at the unit circle here. And to help you, I want you guys to think of tangent being the slope of the radius. Okay? So if I'm approaching pi over 2 from the left, or let's think degrees, 90 degrees from the left, what can you say about these angles? Are they going to be smaller than pi over 2 or greater than pi over 2? If they're approaching pi over 2 from the left, they're going to be smaller. So they're smaller angles than 90 degrees, like 88, 89, 89.5 degrees, stuff like that, that are approaching this. I want you guys to think about what is tangent or the slope of the radius approaching as these angles get closer to pi over 2 from the left. And then do the same thinking but from the right. Okay. So here, imagine this line like this. I'm approaching 90 degrees from the left, so from smaller angles, but it's getting closer and closer and closer and closer. What do you see? What seems to happen to the radius? The slope of the radius. Think about it. All right, and with the usual groups that you guys chat with, let me have you guys check in real quick. Just kind of share bounce off ideas. What do you think? What do you think that's going to be approaching? And go.
One over point something that's small. Like once you get like y equals like y times the next. Oh, it's 1/2. No, I think oh, but it is. Yeah, that actually kind of when it goes from getting why, I guess, I'm assuming why. Why is yeah, that's what I would. I think that's negative. Yeah, that's going out. Or is it just? Yeah, yeah, I think when it reaches pilot I will not all. I think, yeah, like one of the purposes from the. Okay. Why? Because, yeah, from the web, because the way the rotation works. One thing, I think it's negative. So it's not, remember, this is not the graph. And yeah, that's why it's not literally coming out. Yeah. But you're looking at the things as it moves. in this direction, making closer to the negative ways, but at a smaller angle. That's why they.
Value we're coming from less visually.
Yeah, well, we've done values like this for technical things, but this. Positive.
We know that, yeah, exactly, yeah. The negative. Zero over one.
It's still.
No, but one where it's, yeah.
Just this. Grows at 90 degrees.
Yeah, but one of them is zero over one and one over zero. So just a reminder, guys, the angles on the right side are the smaller ones. So this is like 10, 20 degrees. So when it goes to negative, 40 degrees here, 50, 60, oh shit, my scale's way off, but. Yes, the smaller angles are on the right side, but that's why this is a little confusing, because you're approaching this from the left. So these are gonna be smaller angles, smaller than 90 degrees. Okay, so yeah, so you do come from this direction because these angles are smaller than 90. Let's take a look. Let's see here. Okay, so here's the unit circle. Here is tangent at 89 degrees, tangent of 89 degrees. So like 89 degrees is really, really close to 90, right? And it's coming from this side. And right now, tangent of 89 degrees is 57.2228999 and so on. That's the slope of this radius, the big slope, okay? Because it's super steep, right? Super steep. Now, as I get closer to 90 degrees, notice the slope or notice the tangent of that angle. The line keeps getting steeper and steeper and steeper. And so as I keep approaching 90 degrees from the left, from smaller angles, what's happening to tangent? It's getting hella big, right? I did hear some people saying like dividing by 0. Who was saying that? Yeah, what were you guys talking about when you were saying that?
saying it's approaching 1/0.
It's like it seems to be approaching as a slope, right?
Yeah.
The rise is 1, because that's the length of this, and then the run is 0. Yeah, so it seems to be approaching 1/0, but you can't divide by 0, right? But yeah, 1 over a really, really small number is actually giving you a really, really big value. Okay, and visually you can see that the tangent line is getting hella steep. And so, yes, so in this case, the tangent value is going to be approaching positive infinity, because that slope of the radius is getting really, really, really positively steep. Okay. What about as I approach 90 degrees from the right? So from angles that are bigger, let me show you over here. Yeah, so if I do you guys see the slope right now? It's a negative number because the line is going down, right? So it has a negative slope. And as I get closer and closer to 90 degrees, it's getting again steeper and steeper, but with a negative slope. So what do you think this guy is going to be approaching? Negative. Okay. Let me zoom out. Let me go to negative pi over 2, which is negative 90. Let's go from negative 89. Actually, that's okay. So when we're going to look at the graph of tangent, because remember, this is not the graph of tangent, this is just the unit circle. When we're going to start looking at the graph of tangent, I'm going to refer back to this here, which is kind of a complicated part of tangent. Okay. Question? Yeah, bro.
If theta is approaching pi over 2 from the left, why do you try from the right side?
So visually, if I had like the thing is that I don't have a theta axis, right? I don't have a theta axis. It's the x-axis and the y-axis. But pi over 2 is over here, which is really 90 degrees. So as I approach pi over 2 from the left, these are smaller angles, like 89 degrees, and so on, right? But on the unit circle, the smaller angles are coming from the right side. That's what.
Well, if you just look at your arrow above theta, it just
Yeah,
to the left.
it's going, yeah. This notation has to do with, if you look, actually think about it this way. When you look at coming from the left, it just means you're approaching this number from smaller values than that value. So if I was approaching visually, if I was approaching it from coming from this side, see, these angles are bigger than 90 degrees. So that wouldn't agree with what this is supposed to be doing. Okay. Other questions? Yeah, sure.
So as it approaches pi over 2, wouldn't the stopping point be pi over 2?
The stopping point would be pi over 2. But if I tried to plug in pi over 2, right? If I try to plug in pi over 2 here, let me see. If I use this here to plug in pi over 2, and then I use my definition here with sine, that should be sine of pi over 2 and cosine of pi over 2. Right? But sine of pi over 2, this here has the point 0, 1. So sine of pi over 2 is going to be 1 because it's the y coordinate. But cosine of pi over 2 is going to be the x coordinate, 0. And so that's what Cameron and his group were talking about. You can't evaluate it at pi over 2 because you can't divide by 0.
Then why would it be infinity and not undefined?
So infinity is kind of like undefined because it's not a number. It's just telling you it's not approaching a particular number, but it's just approaching, it just keeps getting, it just starts becoming a larger and larger and larger value. Like what we were looking at Desmos. It was like the 57, the slope was 57, and it just kept getting bigger to like 100 and 300 and 400. And that's because visually, the slope of the radius is getting positively steeper. So that slope is growing. And as I get closer to it, it just keeps growing. But I can't look at the slope of a vertical line because on a vertical line, the run is going to be 0. Yeah. Okay? Yeah, in this case, this is undefined. At pi over 2, it is undefined. But this is going to be, I'm preparing you guys for like calculus type thinking. This is not at pi over 2, it is as you approach pi over 2. That's the difference. Yeah, there's a difference between at and approaching because of these weird things here. So at pi over 2, I can't say anything because it's just undefined value as a value. But as I approach pi over 2, this guy, this slope is actually becoming a big, big, big value. Yeah. So I'm going to repeat myself again. It's technically undefined, but it's undefined in a way where it's telling you that the y value, the tangent isn't approaching a number, it's just growing, and it just never stops.
So it's like the process, not the end goal.
Exactly, it's like the process, perfect. It has no end goal, no ending point. It has a process of always getting bigger. While this one, the slope of the line as you approach 90 degrees from angles bigger than 90 degrees, the slope just keeps getting more and more negatively larger. Okay. So now we're going to switch to function notation. So switching to the notation y equals f of x, like the common function notation that we've been using. We're going to let f of x equal tangent of x. So now X here is representing the angles. Okay, think of it as a theta. And then I want to get an idea of the graph of it. So let's put pi over 2, pi, 3 pi over 2. And then over here, negative pi over 2, negative pi, negative 3 pi. Okay. My blue marker here. And then the vertical axis is going to be tangent. So at 0 radians, that means the radius is right here, right? What would be tangent of 0? Let's see, so tangent of 0, let me use this as sideward here. So I got tangent of 0, that's just sine of 0 over cosine of 0, which is going to be 0 over 1. Here, it's okay for 0 to be on the top, right? So that's just 0. And that makes sense because what's the slope here of the radius? There's no slant, it's flat, so it's 0. So that makes sense. Now we're going to use what we just discussed here. And now this will help out the approaching from the left, because now I do have an angle axis. So now it'll make sense to approach pi over 2 from the left. So as I approach pi over 2 from the left, what should happen to tangent? It gets bigger, right, from what we just discussed here. So it's going to get larger and larger and larger and larger. Does it approach a value? No, it doesn't approach a value. Is pi over 2 in the domain of this function? Can I plug it in?
No.
No, it's not in the domain. So it's going to be kind of like what we learned for rational functions. This value is not in the domain because it makes the bottom 0. And because of this behavior, we're going to have, what do we end up having at pi over 2? We're going to end up having an asymptote, like you guys did for rational functions. We end up with an asymptote right here. And that's because the graph, the y value or the tangent values just keep getting larger and larger and larger as you approach it from the left. Now, as you approach pi over 2 from the right, we saw that tangent is going to be approaching negative infinity. Okay. What about at pi? What would be tangent of pi here? Let's see. That's this point over here, right? So it's going to be y over x. There's going to be 0. So we have a intercept at pi. And then from what we discussed here, as I approach pi over 2 from the right, tangent should be going down. The tangent values should be going down. And so, yeah, we're going to end up with a vertical asymptote. And so basically, anywhere where tangent, whatever makes, wherever we get cosine to be 0, this behavior is going to end up something. Okay. Where's cosine going to be 0? At which angles here? All the 90s, right? All the pi's over 2's. So yes, we're going to end up with a vertical asymptote here. We're going to end up with a vertical asymptote here. And a vertical asymptote here. And at all the multiples of pi, 2 pi, negative pi, and so on, we're always going to get tangent being 0, because at these angles, the y values are always 0. 0, pi, 2 pi, negative 2 pi, and so on. So you're going to end up with intercepts there. as I approach negative pi over 2, so now I'm rotating this way. What do you guys notice happens to the slope of the radius? It gets more and more negative. So this behavior is going to copy that. So it's going to kind of do what it did here. So it's going to get more and more negative. And then it ends up repeating that process throughout all of these. So is there repetition that happens? Yeah. Okay, so there's repetition, there's a period. Okay, period. Skip it. What's the period in this case? How often is it repeating? What's the length of it that it repeats? Pi, right? It repeats every pi over 2 to another pi over 2. So a total of pi units it repeats. So in this case, the period is pi. Is there an amplitude for tangent? Is there like a width that we can measure?
Or in infinity to make it.
Yeah. No. So in this case, there's none. So there's none. Okay. So let me add a couple more things that you want to make sure you know for your tangent. Where do we seem to have vertical asymptotes? Multiples of pi over 2. So 1 times pi over 2 is here. What about 2 times pi over 2? What's 2 times pi over 2?
Pi.
So then is that a vertical asymptote? No. So you have to be more specific.
It's at the
Odd multiples of pi over 2. Okay. So we end up with VAs, vertical asymptotes, at odd multiples of pi over 2. The way you're going to write this mathematically is you're going to say when x equals let's go with evens first. Evens, okay. What's true about even numbers? Spit out some facts about even numbers.
N times 2.
Give me some more.
They're always positive.
-2, -4, -6, those are,
Multiplied.
they're divisible by 2. Which also means they're multiples of 2. So if they're multiples of 2, then as Brian said, you can write them as 2 times an integer.
Remember prime?
The only prime one is 2.
It's
It's 2, yeah, it's the only even prime. So in general, if I want to write an even number, I can write it down as 2 times k, where k is an integer. Cool? So then an odd number is not a multiple of 2, but I can think of an odd number as an even plus 1. Right? Like 2 plus or minus 1, either one. 2 plus 1 is 3, 4 plus 1 is 5, 6 plus 1 is 7, and so on. So I'm saying this because this thing that I wrote in English, the textbook is going to write it like this. X equals 2k plus 1 pi over 2. And I don't want you to be like, whoa, what the hell is that? This is how you write an odd number. Okay? Where k is an integer. So if k is 0, I got 1 times pi over 2. K is 1. I got 2 plus 1 is 3. That's 3 pi over 2, and so on. Okay? Where do we have x-intercepts? There's one right there. There's one right there. You can think of it as the even multiples of pi
Or multiples of pi.
or just multiples of pi. Okay, so notice that we have x-intercepts at multiples of pi. So in this case, it's all multiples. So how would I write that with this kind of k notation? Pi k. So, or k pi, however you want to say it. Pi k, where k is an integer. So -1 pi, -2 pi, -3 pi, and so on. I'm gonna give you all those. Okay. Cool. All right, a little bit more. So this is the graph of tangent. That's as much as we'll need to know, okay? On the homework, I think there's like the homework due this Sunday is short because your homework due Friday is kind of long, okay? All they'll have you do is maybe like shift this graph. So you would start out with this graph and then shift it accordingly, stretch it, things like that, okay? Is this graph 1-to-1? Does it pass a horizontal line?
No.
Hell no. Okay. So to define the inverse tangent, like what we do with sine and cosine, we want to turn it 1-to-1. So what was the trick that we did to turn these trig functions into 1-to-1? Say it again?
One period.
We only wanted one period because that will restrict the domain. Okay, so we want to restrict the domain so that it does pass the horizontal line test. So notice that it keeps repeating, like you guys said, at a period of pi. So what the textbook's going to use is that it's going to erase all these other ones and only look at the domain from -pi/2 to pi/2. So it's going to ignore all this and all that and only use this one. And that will turn it on. So for the inverse tangent, or sometimes called arctangent. So we restrict the domain of f of x equal tangent of x to -pi/2, pi/2, but not including them because they're not in the domain, right? They're undefined there. To turn it into a 1-to-1 function. And so from doing this, we can now define the inverse. So we're going to let the inverse of that, of tangent, be the inverse tangent of x, which can also sometimes be written as arctan of x. And so let's see here. I want you guys to grasp it. Okay. So if I'm going to ignore all this part of the, all these parts here, and I only care about -pi/2 to pi/2. So now I'm just using this part of the graph. I want you guys to figure out what the graph of inverse tangent will look like using your knowledge of inverse function. Try to see with your classmates, see if you guys can sketch the graph of the inverse. Okay, let me write that. So sketch the graph. And then I want you guys to find the domain and range.
Yeah.
Remember that for tangent, the horizontal axis is talking about angles. Okay, so the x's here are angles. So when you do inverse function, what's angles? The x-axis or the y-axis? The y-axis should now be angles. Okay, guys, quickly compare with your classmates. Quickly compare. I want you guys to ask yourselves, one, did I graph a function to begin with? Does it pass the vertical line? Okay, your graph has to be a function.
Yeah, that's what I'm. Yeah.
See if you guys can write the domain and range.
Yes. It's literally.
Bring this Y, right? All right, let's see. So here, the x's are angles, right? So for the inverse function, remember x's and the y's, the inputs and outputs swap. So the angles should now be on the vertical axis. They're now the y values. For positive pi over 2 and negative pi over 2. Should be right here, okay? As the angles approach pi over 2, the y values are getting hella big. As the angles approach pi over 2, the y values get really big. So as I approach pi over 2, now the x values get really big. So then you're going to end up with a horizontal asymptote here now. And as I approach pi over 2, the x values get really big. Like that. Okay? Yeah. It includes the point 0, 0, right? So if I swap the coordinates, the inverse function still includes 0, 0. As I approach negative pi over 2, the y values get very negative. So as I approach negative pi over 2, I'm gonna have another horizontal asymptote. The x values get very negative. So it'll go this way. Okay. With this domain restriction, right? With this domain restriction that I have, what's the domain here? What's the interval for my domain? Positive pi over 2. What about the range? Yeah, there's no smallest y value and there's no biggest y value, right? So we're just using everything you guys learned in the first few weeks with function stuff. Okay, this is oh, let me be specific. This is this is the domain of f, and this is the range of f. So what did we say was the relationship between the domain and range of f and the domain and range of the inverse? Well, they're swapped. So then the domain of f inverse is really now the range, which matches, because the domain goes from negative infinity to infinity. And the range of f inverse is now the domain of this guy, which also matches. The y values are in between these two. Okay? Yeah. Okay.
And then why you went down that way and went that way?
Yeah, so let me use some notation that we've been using. So for this graph, as x approaches negative pi over 2, right? From the left, oh sorry, from the right, but let's just say negative pi over 2. What are the y values doing? They're going down. So they go to negative infinity. So then if I swap this, that should be happening here. So as x approaches negative infinity, the y values need to be approaching negative pi over 2. So as x goes to negative infinity, the y values start to approach this y value. So it's an end behavior thing, yeah. Which is hard to say in words, which is why you guys are learning this notation. Yeah. Okay. Okay, let's take a break. We'll stay here. And then after your break, we're gonna go over secant and cosecant, and then I'm gonna have you guys do some problem. Okay? But you guys look very tired, so let's take an early break real quick. Let's come back at 1:47. Yeah, I'll give you guys an extra minute. 11 minutes. Oh, yeah, right. That's 11 minutes. Okay, I'm not tripping. I can do that. Yeah. All right. So let's take a quick break. Think you have an idea? Just check in with a classmate. So I am seeing different answers. Remember that dividing by 0 is undefined, so that's not a good answer. And can you say write something where you're dividing by 0? Okay, let's see. Picked on Logan last time, so wait, I'm going backwards more in the last class. Okay. Victor, any ideas? with the group that you spoke with? Okay, all right, I got to you too early, sorry about that. Bobby,
So the M increases infinitely, either negatively or positively, depending on which direction.
okay, so you're saying we need, so M increases positively or negatively, depending on what?
Which direction infinitely?
On which direction? When you say which direction, what is it, what do you mean by
Like-
that?
Which direction the angle is pointing.
Gotcha, so you're talking about this direction, right?
Yeah,
Okay,
if it's coming in from the negative or the positive.
from the negatives or the positives, yeah, so that's something you do have to take care of. And I purposely didn't write the one-sided limit, the one-sided directions. So yes, you guys have to be careful, if you're approaching zero from the right. If you're approaching zero from the left. Okay. Let's take a quick look. You guys can see this. So here I have a line. My A value, my slope is going to be 1 over whatever this A value is here. So right now A is 1, so it's 1 over 1. As A starts to get smaller, but I'm approaching 0 from the right, notice the value of the slope. So A starts getting smaller and smaller and smaller and smaller. And what seems to be happening to the slope? It's getting bigger and bigger and bigger. So most of you walking around, I saw that you noticed that it's getting bigger and bigger and bigger. But as you approach 0 from the left side, what's happening to the slope now? Is it getting bigger? It's getting like bigger, but in the negative version, right? So it's getting more negative. Yes, so that matters because this tells you that as you approach 0 from the right, this denominator is getting smaller, but from positive value. So the slope blows up, but positivity goes up. Okay. Versus if you're approaching 0 from smaller values than 0, so therefore negative values, the slope also gets really big, but it gets really big in the negative sense. Okay. So yeah, so whenever something's approaching 0, and in general, when you have a fraction where the numerator is some number, but the denominator starts to get smaller, you got to be careful of how it's getting small, because it'll either get really big or really negative. Okay. Let me stop sharing. All right, so this is going to apply. Pass up your warm-ups. Thank you. We use that. We're going to use this here for the secant and cosecants. I apologize that today it's more me talking. But I'll stop in a little bit. Thank you. Thank you. Okay. All right, guys, so let's see, let's talk about secant and cosecant. We're going to start with cosecant. So graph of cosecant. A lot of graphing today, I know. All right, so let's see, we're going to define our function here to be cosecant of x. Which we know is a reciprocal of sine, right? Remember, if it's C, it's the opposite, S. And with S, it's the opposite, it'll be C. Okay? So like what we did with tangent, we don't want our denominators to be 0. So we don't want sine to be 0. At which angles is sine going to be 0? 0, 180 or pi, 2 pi, 3 pi, all the multiples of pi. And the odd multiples as well. Okay? So because of that, we're going to end up with vertical asymptotes. Okay? And that's because we're going to be approaching 0. Just the way this is going to be approaching 0. So it's either going to be approaching positive infinity or negative infinity, which produces a vertical. Okay, so we end up with a vertical asymptote at x equaling multiples of pi, where k is an integer. Remember, this just means multiples of pi. Multiples of pi. So if I want to leave some room down here in your notes, if I want to get an idea of what the graph of this is going to look like, let's write down the usual angles: pi over 2, pi, 3 pi over 2, 2 pi. And the same thing here. 2 and 2 pi. We know that multiples of pi are going to be undefined. We're going to end up with asymptotes. Okay? So let's just quickly do some more arrow notation remarks. I want to give you guys as much practice with this arrow notation as I can. Let's see. Let's just do one of them. Or let's start with one of them. So let's start with just pi, the first pi. We're going to approach pi from the left. Okay. Oh, sorry, hold on. Before we do this. Let's see. To start graphing cosecant, what's going to be very, very helpful is to actually graph sine. Okay. So if we graph sine first, let's use the knowledge that you guys learned on Monday. Let me make the one down here a little bit smaller. If I graph sine from what we discussed on Monday, sine will be 0 here and then 1 here, 0 here and then -1 here, and so on. If I graph sine like this, then we use the fact that cosecant is 1 over sine. And as I approach pi from the left, what is sine approaching? Approaching 0. Okay, let me slow down on that one. Okay. All right, let's do it again. So as I approach pi from the left, coming from the left, what are the values of sine approaching? They're approaching 0. But are they approaching 0 from values greater than 0 or less than 0? Greater than 0. So how would I write it? I'm approaching 0 from values bigger than 0. Plus from the right, or plus and positive.
So that would say, as it approaches from the left, it zero.
You're approaching it, your sign's approaching zero, but you're being more descriptive. It's approaching zero from positive values. Because the graph comes from the top. Right? Yeah, right.
Did you say for that we can put it on what is it?
WebAssign will not have you do this. I'm doing this on purpose because I want to give you guys as much notation of this for calculus. Because this is where students get all confused and tough, right?
They always think of women
Yeah. Exactly. Now, cosecant is 1 over sine. So it's like we're approaching 1 over something approaching 0 from the positive side, the way this was doing, right? So if I'm approaching 1 over 0, where I'm approaching 0 from the positive side, the overall fraction is going to be approaching positive infinity. So this whole thing, which is really cosecant, is going to be approaching positive infinity. So it's like this chain of logic that's happening. So as I said, let me use blue actually. We're going to end up with vertical asymptotes at multiples of pi. Yes.
How is cosecant approaching positive infinity when it's not going higher than 1?
Well, it is going to go higher than 1. Sine doesn't go higher than 1. But the cosecant is 1 over sine. And this
Oh,
thing,
we drew sine, right?
yeah, this guy's approaching 0 from positive values. So whenever I have 1 over something approaching 0 from positive values, like you did on the warm-up, the overall fraction goes to positive, gets really big. So therefore, this fraction gets really big, which means cosecant gets really big. At pi over 2, what's sine of pi over 2? 1. So what's cosecant at pi over 2? 1 over 1, which is just 1. Okay. So we know cosecant coincides at that point. But from what we discussed here, as you approach pi from the left, cosecant is going to end up getting really big. Zero is a multiple of pi. So there's also vertical asymptote here. So let's do this one real quick. As x approaches 0 from the left, what is sine doing? What value is sine approaching? It's approaching 0 from positive or from negatives? Positive. So again, it's doing this. It's approaching 0 from positives. So therefore, I have 1 over something approaching 0 from positives. So again, cosecant goes to infinity. So then that's going to force now this side as I approach 0 from the left. Oh shit, from the right. From the right, I apologize. I'm approaching 0 from the right. Cosecant also goes up. Questions on that?
Is that
It does not make an actual parabola, but it looks parabolic, but it's not an actual parabola. Okay, pi, I can't plug in pi because then that would give me 0. So that's not in the domain. So now let's go over here. What's sine of 3 pi over 2? Sine. It's -1. So what's cosecant of 3 pi over 2? -1. So that also coincides with the point there. So now I'm not going to write all this stuff. As you approach pi from the left, what is sine doing? Approaching 0, right? But from negative values. So it's approaching 0 from negative values. So what happens to the overall fraction? It goes to negative infinity. So what's going to happen is cosecant now is going to shoot down towards negative infinity. And the same logic is used here to show that this goes down to negative. And then that pattern will repeat. Okay. So here it coincides at that point, and it shoots down to infinity, coincides with this point, and it shoots up to infinity. And so the real graph of cosecant is the blue one, and not the green one. It's the blue one. But my tip is graph sine, and that'll help you figure out where cosecant is. This is going to be flipping upwards wherever these peaks and valleys are at. Okay? Where's my? Does it repeat? Oh, yeah.
Does it work that way because, you can cross horizontal, but you can't cross vertical asymptotes?
You can cross horizontal, but you can't cross vertical asymptotes, yeah. Because vertical asymptotes happen because those values are not in the domain, so that's why you're not allowed to cross.
So are only separate functions because those two can exist in the same function?
Well, it's still a function because it passes the vertical line test,
But not through those two.
but it's not a one-to-one function.
Okay,
Yeah, so it's a function, it's just not one-to-one because it fails this test here.
oh, vertical, right, yeah.
Yeah, and it's not like only one of these is the function of cosecant. All of these, like all these repeating little parabolas will be the graph of cosecant. And so does it repeat? Yeah, right. What do you guys think the period is of repetition? How often does it repeat?
Pi.
Okay, so if it's pi,
2 pi.
then this better be here, right? But it's not. So it's really 2 pi. Because every 2 pi, it goes up and then down, up and then down, up and then down. Yeah. So the period is really 2 pi here. So this has a period of 2 pi.
Doesn't it also have an amplitude of 1?
It doesn't have an amplitude, no, because it doesn't have like a width. It's just shoot off to infinity. Look,
Would there be a way to know that it comes up and then back? Besides,
like with all this stuff?
Yeah.
No. So that's why I was saying the tip I have for you is graph cosine. Wherever cosine is positive, cosecant goes positive infinity. Wherever sine is negative, cosecant will shoot down to negative.
in the origin between these works is its highest point.
It's exactly. It happens at where the cosine is 1 and where sine is positive 1 and where sine is negative.
So essentially, we solve the problem because you're saying we should attempt to solve for sine and then actually solve.
Graph sine, correct, yeah. So in a little bit, we're gonna do secant, and then I'm gonna give you a worksheet. And then I'm gonna have you graph transformations of cosecant. But the way you'll start is just graph the transformation, the same transformation, but apply it to sine. Graph that, and then you know where your peaks and valleys will be at in the period and everything. Yeah. Because it's scary to do it straight from here, but it's less scary to do that same transformation to sine, which is what we did on Monday. And so similarly for the graph of secant, let me have these here. I'm almost done with the lecture part, guys. Then I'll have you guys play a little bit. We got secant, which is really 1 over cosine. So in this case, we're gonna have vertical asymptotes wherever cosine 0. Where's cosine 0? Pi over 2, 3 pi over 2. So all the multiples of pi over, all the odd multiples of 3 pi over 2. So we're gonna have at x equaling 2k plus 1, like what we wrote earlier, pi over 2. And this means odd multiples of pi over 2. So if I want to start graphing it, I'm going to do the same kind of trick and start by graphing cosine instead. And so we know we're going to have vertical asymptotes at all the odd multiples of pi over 2. So we're going to have one here. We're going to have one here. We're going to have one here. And so to help us, back to your question, Logan, we're going to graph cosine first. Same thing, the same pattern, wherever I have peaks and valleys and things like that, okay? So remember, cosine is 1 at 0, so it starts here, and then it shoots down here, then to -1. So cosine looks like this. And similarly, as we did here, to start graphing secant, at 0, cosine of 0 is 1, so secant of 0 will just be 1 over 1, which is 1. And so everything, all the logic we did here, guys, I'm not going to repeat it, but the same logic applies here. When cosine's positive, secant shoots towards positive infinity. And when cosine's negative, secant shoots down to negative. And so on. Same pattern as that's what we did. Does it have the same periods?
Yes.
Let's see. How long is this right here? This distance? Pi, another pi. So yes, it also has a period of 2 pi. Yeah, let me see what time is it. Cool. All right, this next example is what you're gonna do in your homework. And then slow me down here, ask questions. For what? It'll look something like that. It'll say graph f of x equaling 5 cosecant 2x. Yeah. What we're gonna do is use the same strategy we did here. Before I graph that, let me graph its corresponding reciprocal function with the same transformations. So to start, is instead start with its reciprocal function and apply the same transformation. That means I'm going to graph y equals 5. What's the reciprocal of cosecant? Sine 2x. I'm going to do kind of the same function, same transformations, but I'm going to do it to sine. And graph that just the way I did here. And once I graphed it, then wherever sine's positive, I know that cosecant will shoot up. Wherever sine's negative, cosecant will shoot down. All right, help me out here. Let's do the same thing we did on Monday. What's the period of sine here? It's gonna be 2 pi divided by my b value, so 2. So the period's pi. What's the amplitude? 5, whatever this a value is, right? Okay, let's see, let's start with our 4. 1, 2, 3, 4. So I can write pi over 2, pi, 3 pi over 2, and just divide everything by 2, right? Like what we did on Monday. I'm gonna show you a different way. Or you instead start with the period. So the period's supposed to be pi, right? I know the period has to be pi. Therefore, I half that to get halfway point. So what's the half of this? Pi over 2. And then this one is half of this one. Pi over 4. You see that? So I know my period is pi. So halfway is half of that. And then a quarter of that is half of this one. So how long are my increments? Pi over 4. Pi over 4. 2 pi over 4 is really just 3 pi over 4. And then 4 pi over 4 is just pi, right? But basically, as long as you know your increment, that's all you need. After that. So then what would this one be? Basically, this negative of these, right? Okay. And what's my amplitude? 5. So let me just put the 5 here. Any shifting happening? No. So I don't have to worry about that. So now I'm going to graph sine. I know that the sine is going to start at the origin. Then it's at this value, it's supposed to reach the highest point. In this case, it's 5. And then it goes back to 0. And then 3/4 of the way, it reaches the most negative value. And so on. Yeah. So where do we end up having vertical asymptotes?
Wherever it causes that.
Wherever it crosses an x-intercept, because that's where this sine function will be 0, right? That's where this guy's going to be 0. And this is a reciprocal of this one, so I don't want this to be 0. So therefore, wherever I have an x-intercept, I'm going to have my vertical asymptotes. We're applying the same logic we did to this guy. And then here, sine of pi over 4, if I plug that in here, what is the y value supposed to be here? Supposed to be 5, right? Yep. So then this guy, remember, it's really this. It's okay, I'll write that. It could be more confusing. So it's going to follow the same pattern. So the cosecant function is going to align at that point, and then it's going to shoot up to positive infinity, align at this point, and then shoot down to negative. So as long as you can graph the transformation of sine, then you just will do the positive values to shoot up to positive infinity to negative. Okay. Okay. Let's see. Any questions? You guys hella eager to try it? You're like, dude, give it to me. I'm gonna do it right now. All right. If you're not, I'm sorry. I'm gonna have you do it anyway. The homework problems will look like this, so I want you guys to practice that. Thank you. Super fun. You're doing good. All right, let me see. Ooh.
1, 2, 1, 3, 3. And then I divide you two. This one?
Oh, you got it, you got it? Okay. So let's try some of these out. Also, guys, notice that the period of the cosecant function is the period of the sine function. Okay, so the periods will align. We'll go around, guys, and have your questions. Oh, just. Correct. So, the same person, we got really familiar with it. And so we review transformations. So remember, this stretches the filters the function vertically. This one does the opposite. If I see a 2 here, it really divides the 2. Remember that? Okay. So we apply all that to these parent functions. And so what we found here, I'm using sine. So I know I'm going to use the function sine. And this 3 tells me that the y values get multiplied by 3. So it stretches it by 3. And therefore, the amplitude will always be the absolute value of this A. And the period, because the original period of sine is 2 pi, right? If I have a b in front of the x, all these x values get divided by b. But then the period gets divided by.
So it would be 2 pi over 6.
Correct. Yeah, the period would be 2 pi, whatever the b value is.
And then the amplitude would be 4.
4, correct.
Thank you.
Oh, here, and I'll put solutions as you guys are working that out. Do that real quick. Correct. Yeah. Bless you. Salud.
All right, let's see, sequence, there you go. All right, guys, I'm gonna put a little bit of lo-fi music. Since you guys are a little bit more on the tired side today, and less chatty. Yeah. It does, yeah, so. In this case, so go back to the notebook. So for some, the common pattern of change is that it starts with zero, and it goes up to its highest value at a quarter of the way. And when it goes back to zero, when it goes to its most negative value, it comes to zero. This happens at the third. So what we do in this problem. The period has to be the.
Yeah.
Here, I then have to figure out what system. They have different pathway.
Yeah.
To the right system. Yep. And then where's the path of this one? I did it. So then one path of them.
So,
Three paths.
so it doesn't matter like, whatever period we always divided by two. from these two.
Yeah, because this is the looking supports. So actually, it's always happened here.
Okay,
And then this is always happened this. Yeah, so then, now you know that each like increment. Increments are the-
got
So one carries the four.
you.
The two carries the four. That would be this three. Three carries the four. And in this case, it's only these three. And then the negative.
Okay.
For the 15 of the brand. Yeah, but this one is here. Then we go on about that. The period will still be called, it's just that it won't, like, it won't. It won't follow this pattern because everything was shifted. But the period will still be, it'll still repeat every pi rate. So. Where, you know, whatever the numbers are using. Yeah. That's. Like. The same, you keep them the same, yeah. Mhm. Yeah, this is kind of hard. As long as you don't make them. Oh, yeah. Oh, I wish no. Somebody all of that.
I should have said. Yeah. I think it's like where the. Okay. They wasn't spent by nothing, money, but one of the things. We don't know what the field will have to do. Do I go by it? Yeah.
You know, this, so like,
Okay. We've been. Okay, so if you over here. I'm not saying it's wrong.
Okay. Okay, let's see that. No, but that's just my husband. I was just combined. Control like the. Yeah, I think so. Yeah. Yeah. I think that there's a very divine, sign of all sorts. Yeah.
Hold on, guys. I have a quick trig comment. Little trig comment real quick, and it has to do with your past trig class. And I've even talked to the instructors about it, but let's see, so. In your past trig class, you guys usually wrote, you wrote it like this, right? Right? Versus the way I'm doing it here, I'm writing it like this. So here it's factored, here it's not factored. Okay, so in your past trig class, when it was not factored, there was a shift. I think they were calling it phase shift, right? But what was the phase shift here? It wasn't C. It was C over B. Minus C over B. Yeah, it shifts, right? But the reason I'm not writing it like this here is because this aligns with what we discussed with function transformation. Without trig, like any function. So without any function, I mean, with whatever function I'm doing the transformation, what's the shift? C. So in this case, I'm doing this notation because it aligns with function transformation notation. So here, the phase shift is C. You shift left in this case. Is C. In factor form. Okay. Or if you want to go back to how you did it in trig, just multiply this out. And then it'll be like this. Yeah, you don't have to, but if you multiply it out, it'll look like this, right? So then you apply what you learned in trig, and then you say the phase shift is whatever this number is divided by this number, which is again C. If you want to do it that way, okay? But the reason I have it factored is because it aligns with our function transformation discussion.
Why is it shown like that in this circumstance? It is B of C.
Why is it shown like this? I'm not really sure. I've asked several instructors that have taught just trig by itself. And I think it's because the textbooks teach it that way. The trig textbook. I don't like it because then when a student sees function transformation, it's a little bit like counterintuitive. Yeah. So that's why I leave it factored so that it matches this notation.
Why carry factor? It's like it's C doesn't have a B next to it.
If I want to rewrite this in this form, I would have to factor the B out. But for me to factor the B out, I take out the B, but now as a consequence, what can I multiply here so that I get a C? And it turns out to be C over here. Yeah, and so that's why the transformation, that's where they shift is really this value. Which is not obvious when you look at it as a function transformation. Okay, guys, we're gonna end early. That's it. That's all I have for you. Okay? So we're gonna end on an early note today. Yeah, and I'll stick around, guys, if you have questions.
Otherwise, it's gonna be the.
No,
Oh, yeah.
they don't care.
It's true, though. It's in part elevated, you know, like, yeah, like this. And you got it. Well, it's really- why is it- yeah, there have been the middle. Well, it's not- I didn't see it. Here's the better you want to be on. So it's- I can go in and I love each other. Yeah, they should run. Yeah, but all the shit. So,